All right, now that we have the background done, we're actually ready to go ahead and find those confidence intervals on our own from start to finish. So learning how to find that error piece and then again, how to put it all together. So the difference between the point estimate and the actual parameter value is called a sampling error. So when the population mean is estimated, the sampling error is the difference between the sample mean and the population mean. Now, in most cases, of course, the population mean is unknown and the sample mean varies from sample to sample, right? So if you actually know the population mean and you know the sample mean, then you can subtract them and find the sampling error. But a lot of times the sampling mean is unknown. So we can't always do that, but we do know that it exists, that there is some sort of sampling error that's going to be there. You can calculate the maximum value for the error when you know the level of confidence in sampling distribution though. So if I know the level of confidence that I want to use, let's say it's 95%, there is a formula I can use to find the maximum error. So then I have, again, a reasonable interval that I can look at. And this margin of error changes depending on your confidence level. So that's why it's important to choose your level of confidence first. Like I said, most times we tend to choose 95%. That's very common, but usually 90 and 99% are also common as well. So you may see those occurring a lot too. And you can use other values too. Those just tend to be the most popular. So 95% we like because we have a high level of confidence in our interval, that it actually includes the true population mean. But again, that 95% is an interval that's not so wide that it is not useful. So it's still it's a good useful interval. So given a level of confidence C, the margin of error, which is sometimes also called the maximum error of the estimate or the error tolerance, again, you kind of see that one more, is the greatest possible distance between the point estimate and the value of the parameter it is estimating. So for a population mean, when sigma is known, so remember, sigma is the population standard deviation. Okay. The margin of error is given by this formula here. Now, I want to make a very clear distinction. So in section 6.1, we are assuming that the population standard deviation is known. So it's not estimated, it is actually known. So how would you know this? Probably because someone has already done research on the subject and they already have data there. So there would be some sort of research already done where you know the population standard deviation already. Or maybe you have a population that you have dealt with. So if we're looking at maybe like a company or someone where they actually have all the data on every employee for, let's say, their salary or something like that, then maybe they actually do have the population data. But it's really important to know that this formula only works if you actually know the population standard deviation. In section 6.2, we'll show you a little bit different formula where that you can use when you do not know the population standard deviation, which is more common. So your error is found by this formula here. So you're going to use that Z that we just found. You multiply it by the population standard deviation, and you divide it by the square root of n, where that is your sample size. Now, before you can do all this, you have to check two things. You do need to have a nice, simple, random sample, or at least random. And this is really important to check. At least one of these has to be true. So either the population is normally distributed or your sample size has to be at least 30 for this to work. And the reason this works is because of the central limit theorem. So if you go back to chapter 5 in the central limit theorem in 5.4, you'll remember that we either had the population was normal or your sample size was at least 30. So those same restrictions are here too. And if you don't have those restrictions, then you can't use this formula. So this formula, again, is only valid if one of these two things, either a normal population or a large enough sample size, occur. All right, so let's use the data in example 1 and a 95% confidence level to find the margin of error for the mean number of hours spent on the athletic activities. And we're going to assume that the population standard deviation is 2.3 hours. So if we go back to example 1, we found before that our sample mean was 21.1 hours. We also know that we're using a confidence level of 95%, and we saw in the last video that your Z value there is what, 1.96. Just double check here. Yeah, 1.96 there. So here is my formula for the error. So that means the error then is going to be that Z value times my standard deviation over the square root of n. Now also remember that in the original example, we had 40 students that we surveyed. So your n is 40 here. So the error is going to be 1.96 times the standard deviation of 2.3 divided by the square root of 40. Now, for here, you're definitely going to use your calculator. And the biggest thing is just to watch how you type it in. So you can do 1.96 times, and then if you want, you can put this in parentheses. So 2.3 divided by the square root of 40. And then you can close your parentheses, and then at least that way you know that it's in the right format. And then we can hit enter, and we get about 0.712777, etc. Now your book rounded to one decimal place here, so our error was about 0.7. So that's how we're calculating the error here. So how do you actually find the confidence interval? That's going to be the next step. So for this one here, we're finding that error. And then we can also go ahead and find that confidence interval. So for confidence intervals, at this point, it's going to be really simple. So all we're going to do is we're going to take that point estimate in the middle, and we're going to add or subtract our error to it on both sides. So that gives us an interval. And you can see that right here. So the confidence interval, for the population mean is to take that point estimate, which is your sample mean, and add and subtract the error. That's all we're going to do, which we actually already did before. Now, this kind of runs through all the steps again, kind of putting the whole thing that we've done together. So when you're doing a confidence interval for the population mean when sigma is unknown, again, the first thing you need to do is make sure you actually know sigma. The sample is random. And again, either the population is normally distributed or your sample is greater than 30 or 30 or greater. Here our sample size was 40, so we were fine. You do need to find your n and your sample mean if you haven't yet. So you could go through those calculations and find those like we did in example 1. Then you're going to go ahead and find that critical Z value. And again, we went through the process there on how to find it for the 90%, the 95%, and I gave you the 99%. Those tend to be the 3 most common, although you may see other examples too. And now at this point, we found the error, and now we're ready to add or subtract to get the interval. So I'm going to take my mean and I'm going to add the error. So I have 21.1, and I'm going to add 0.7. And then I'm going to take the mean and I'm going to subtract the error. C4, 0, 2. So I have 20.4 and 21.8, and this is going to be my interval. So then my confidence interval is going to be 20.4 to 21.8. Okay, so this is our confidence interval for this problem. I know we kind of estimated before we used 0.6 for our error, just kind of guessing, but this is the official formula now. So 0.7 is actually the true error that we're going to do here. And this is going to be our final answer here for our confidence interval. And again, this is one way we can write it. Let's do a few more examples here. Okay, so I actually already did example 3 on the previous page. So it asks us to find that confidence interval for 95%, which we already did. So we did example 3 at the bottom of the last page. So let's do example 4 now. Let's try a 99% confidence interval for the mean number of hours. And I'm going to do it by hand, and I'm also going to show you how to do it in the calculator, which is obviously much faster. So I'm going to do the 99% confidence level. So if we have 99% confidence level, then our Z value, we have already seen, I gave this one to you guys, is going to be 2.575. Our X bar was 21.1 and our N was 40. So the error here, again, is that Z score times your standard deviation or the square root of N. So we have 2.575. Our standard deviation was given in the last problem. It was given as 2.3. And then we're dividing by the square root of 40. So I'm going to take out my calculator at this point. So I have 2.575. I'm multiplying that by 2.3 divided by the square root of 40. And I'm going to get that the error is about 0. And it says 936. So using one decimal place, I get 0.9. Now we want to do the full confidence interval. So I'm running out of room. I'm just going to come down here a little bit. So we're going to take that mean and we're going to add the error. So 21.1 plus 0.9. And then we're going to take that mean and we're going to subtract the error. So 21.1 minus 0.9. Okay. So a lot of this you could probably just do in your head, but if not, take out your calculator. So you're going to get exactly 22 or 22.0 there. And then here we're going to get 20.2. So our confidence interval here is 20.2 to 22.0. Now, do notice before we go on that the width here of the interval, it's wider than the previous answer. So our previous answer was 20.4 to 21.8. So at 95% confidence, we were at 20.4 to 21.8. And at 99% confidence, that interval is wider now, 20.2 to 22.0. So to gain more confidence, you have to make that interval a little bit wider so that, again, you feel more confident that that true population value is in between here. Now, we can do this on technology very quickly here, just finding that confidence interval. So I think this is a nice one to learn. So what you're going to do is I have the steps written right here for you. You're going to press the stat button. Then on the top, you want to go over to test this time. And there's a ton of different tests. You want to make sure you're careful which one you select. When sigma is known, like in this section, you're going to select Z interval. So I can see it right here, Z interval. And then you're going to enter some important information, right? You're going to enter the sigma, which is 2.3. You're going to enter your sample mean, which was 21.1. You need to enter the 40 for the sample size, and you're going to enter your confidence level. So my confidence level here is 99. And what you'll see on the right, once I hit enter, so I just hit enter, it will adjust, and this is my confidence interval right here, right? So it's saying my lower bound there, my lower level is 20.16. My upper is 22.036. And if you round those, you do get the 20.2 and the 22.0 that we had over here doing it by hand. So that calculator, again, it can be really nice and fast for you to get through. Let's do another one with the calculator for this one. So a college admissions director wishes to estimate the mean age of all students currently enrolled. In a random sample of 20 students, the mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years. So again, that's the population standard deviation. So it's 1.5 years. And we are told the population is normally distributed, which is good. Our sample size is only 20, right? So remember your requirements. If it's less than 30, then the population has to be normal, or you can't use this formula at all. So you just want to be careful. And again, it's kind of written again here on the guidelines at the bottom of the page before. So you do need to make sure that we have a random sample, which again, we're going to assume this was done correctly here. But if our sample size is small, like it is here, then the population must already be normally distributed. And the other thing, remember, that we're doing in this section is we already know the population standard deviation. So in this case, it was known from a previous study. All right, and we're going to construct a confidence level interval of 90%. So I'm going to do this one on the calculator. And again, I'm going to just follow these steps. I'm going to hit stat first, then over here to tests, and then I want Z interval. Now I'm going to enter my information. So my sigma is 1.5. My mean is 22.9. My N is 20 here, and my confidence level is 90. So I'm going to hit enter, and then you should see your interval right here on the right. So my lower value is 22.348, and my upper value is 23.452. And let's see, we're going to round this just to 1 decimal place. Yeah, we'll do 1 decimal place here. So we're looking at about 22.3 to 23.5 for our confidence interval. And again, if you want to do this by hand, you absolutely can. So we have all the information we need. The only thing we're missing is that Z, but we know it. So when it's 90%, that Z is 1.645. So that's one of the most common ones. Again, the 90, the 95, and the 99% are common. So those are ones that you should already have your Z values ready to go. For the other ones, you'll have to draw the picture and figure out the Z values on your own if it's something beyond that. So here you have it here. Now here they did it by hand, so they were able to find the error was 0.6 and add and subtract from there. So that's just, again, a different way that you could do it if you want to use the formula by hand. Now I want to talk a little bit about the interpretation here about what a confidence interval and a confidence level does for us. So here we had a 90% confidence level, right? So I just want to read through this interpretation, which is really important. After constructing a confidence interval, it's important that you interpret the results correctly. Consider the 90% confidence interval constructed in this example. The population mean is a fixed value predetermined by the population. It is either in the interval or it is not. It is not correct to say there is a 90% probability that the actual mean will be in the interval, or there's a 90% chance. That is not the correct interpretation. This is a wrong statement because it suggests that the population mean can vary, which it cannot. So the correct way to interpret this confidence level is to say the following. With 90% confidence, the mean is in the interval 22.3 to 23.5. Right? Another way to say it is I could say, I feel 90% confident that the true population mean, which is mu, lies in the interval, and in this case, the interval is 22.3 to 23.5. Okay, so this is really important here. I know it seems kind of silly and maybe not important that the wording is correct, but it is. So our interval here is not a statement about probability. It's not about the fact that there's a 90% chance that the mean is in that interval. That's not what it is. We're saying that we're 90% confident that the mean is in that interval. So there is a 10% piece of that we're lacking in confidence where it may not be. So you want to make sure you're wording things correctly. Something like with 90% confidence, or I feel 90% confident that, those are all correct statements. And you can exchange that with 95% or 99% and so on. So you want to make sure you don't say things like there's a 90% chance that this interval contains the mean, because that's not what we're saying. We're saying we feel 90% confident that the value is in the interval. So it's about our confidence in the interval, not about a probability here. Another thing to think about here is just a nice little picture. So the horizontal line segments represent 90% confidence intervals for different samples of the same size. So remember, if you're sampling from a population and you were to do samples over and over again, you're going to get all different means, right? They're not going to be the same mean for each sample. You get different values depending on who was in that sample. So another way to kind of think of the confidence interval using 90% is that in the long run, 9 of every 10 such intervals will contain the mean. So for instance, here's an example of 10 different samples. So you can see the true mean is at this line here in the middle. So let's pretend that's the true mean. Now this sample has its mean here, this one here, this one here. All those dots represent the mean of the sample. So you can see that the mean of the samples is close to the true population mean. And when we include the interval, so the interval will be that little segment there, that yeah, it is going to cover the true population mean, right? It's going to be somewhere in there. Now, every once in a while you get a sample, of course, where that doesn't happen. So here's your example where there are times where you get a sample where you think it's a great sample, you've done everything right, but it just doesn't contain the population mean. So that 90% confidence, again, also kind of says, think about 90%, that means 9 out of 10 or 90 out of 100 samples, the confidence interval would contain the population mean. And then in 10% of the samples, it would not. All right, so one thing I want to help you guys figure out is sometimes it's helpful to work backwards. So there could be an example where you're given the confidence interval, but maybe you need to work backwards and find the point estimate or to find the error. And this can be true with technology. So maybe you're answering a question on technology and you found the confidence interval and now the question's asking you for the margin of error. And you're like, well, I didn't do that. I didn't use the formula. I used the technology. So how can you work backwards? So it's actually pretty simple. So here's a confidence interval that was already done. Okay, so the first thing we can do is we're going to find the error. So what you're going to do is subtract. So you're going to subtract the upper and lower values in the confidence interval. So we're going to take that 14.8 and subtract it with the 12.0. And what we're going to get here is 2.8. And then what you're going to do is divide it in half. So we're going to do 2.8. We're going to divide that in half and we get 1.4. So your margin of error here is 1.4. So you just take the length of that interval, cut it in half. There's your margin of error. Now, how do you find the point estimate? There's different ways to do it. One way to do it is just take that margin of error. So you can take your upper value and subtract the margin of error. So if I do that 14.8 and subtract 1.4, I get 13.4, and that would be my point estimate. So that would be your mean in this case. You can also add it from the lower value. So if you did 12.0 plus 1.4, you'll get 13.4. So that works too. And the other way you could do it is you could find the average of these two values here. So if you were to take, that 12.0, add it with the 14.8 and divide it by 2, again, there's that 13.4. So there's lots of different ways to find that, that mean in the middle. You can either use your error and either subtract it from the top or add it to the bottom, or you can just take the average of the upper and the lower. So 3 different ways that you could find that point estimate there. But it's actually pretty quick to work backwards. So if you're using technology to find that confidence interval, but then you also need to give your answers for the error and the point estimate, then working backwards may actually be faster. So just a little tip. All right, the last thing here is sample size. So for the sample statistics, as the level of confidence increases, the confidence interval widens, right? So we've said that as it gets as you go from 95 to 99% confidence, for instance, that interval gets wider. So the precision of estimate decreases, meaning it's just not as precise. So one way to increase precision is to increase the sample size. But how large of a sample size is needed to guarantee a certain level of confidence for a given margin of error? So when you're doing confidence intervals, you still have that cutoff of a sample size of at least 30 or a population that is normal. So you do have that floating in the background, right? But that's just a very basic criteria that you have to meet. We also want to make sure that our sample size is big enough, right? What if my population is normal, but my sample size is only 5? That may not be big enough still, even though it fits the criteria for using the formulas for confidence interval. So you want to match those requirements with also the sample size requirements. So we do have a formula to use that tells us how much data we need to have for our sample so that it's actually valid as well. So you need both of those things really when you're doing your confidence intervals. So again, you're choosing your confidence level, and we would then have our margin of error. The minimum sample size needed to estimate the population mean is given by this formula here. If n is not a whole number, we do always round up to the next whole number, otherwise you'll be too small. And in this case, if sigma is unknown, you can estimate it using the sample standard deviation, assuming that you already have a random sample with at least 30 members. So you could use previous data that you've already had, or if you started collecting data already, you could use the first 30 or 40 data points you have and find the sample value that way. So the researcher in example 1 wants to estimate the mean number of hours on required athletic activities by all student athletes in the conference. So how many student athletes must be included in the sample to be 95% confident that the sample mean is within 0.5 hours of the population mean. So this is our confidence level. And this right here is going to be the error that we want. Now, this may be different than the error that we just calculated. So here he's kind of going into it saying that, okay, we want our error to be 0.5, which is different than before when we were calculating the error and we got 0.7, right? So that error was 0.7, which isn't 0.5. So here we're kind of going in before the study and saying, okay, I would like my error to be 0.5. What sample size do I need here? Okay. So I'm using this formula. Now we're doing that 95%, so I know my Z is going to be 1.96. From before, we saw that the sigma was about 2.3. Okay. And again, here he's telling us he wants his error to be half an hour. So what we get is 1.96 times 2.3, and that's all divided by 0.5, and then the whole thing is squared. So you just want to be careful here. So I'm going to do that 1.96 times 2.3 first in my calculator. So I'm doing that numerator. Then I'm going to divide it by 0.5. So I'm getting 9.016, and then I'm going to square that. I'm using all the decimals here. So square it. So I get n is equal to 81.288, etc. So I always round up. So your sample size has to be at least 82 here if you want an error of 0.5. So think about it. His sample size was only 40 and his error was bigger, right? Wasn't it 0.7? So you kind of can think about beforehand, okay, I want to be this confident and I would like my error to be only half an hour. So you're kind of keeping that interval smaller. So he would need more people. He only has a sample of 40, which is why his error was bigger at 0.7, so his interval was wider. If he wants to have a smaller, more precise interval with keeping it still 95%, then he's going to have to increase the sample size. So there are two ways to get more of a precise interval. One is to lower your confidence, which is not great because you don't want to lower it too much, and not have a strong confidence there. You want to be usually at least in the 90s. So the other way to get a more precise interval, so it doesn't just keep getting wider and wider, is to increase your sample size. So if he wants to narrow that interval to only 0.5 error, not 0.7, he's got to get 42 more people in his sample. Okay. So for confidence intervals, again, the thing that you really just want to remember is, first of all, it's just an estimate for the population value. So we're taking a sample and we really want to know about the population, right? Because I have my sample data here. Maybe I only have the 40 people, but I would really like to know about everybody at the conference. So I take my sample information and then I can use those formulas and get an interval so that hopefully I can kind of get a better idea of where that true population mean actually is. And then we want to remember that the interval is based on our chosen level of confidence. Now, in my math lab, they'll tell you what to use, but in reality, most projects use 95%, some 90, some 99%. Those are the most common. And again, because we want a high level of confidence in our interval, right? We want to be confident that the true mean is actually in there, with also balancing precision there. So when you interpret your interval, you just want to be careful and remember that we're not saying that there's a 95% probability that the mean is in there. What we're saying is that we're 95% confident that the mean is in there. And there is always a chance that it's wrong, right? So, and it's not necessarily that we did work wrong. So our math could be great, our sampling technique could be great, but sometimes it just happens where your sample doesn't represent your population. So hopefully it doesn't, right? If you have a 95% confidence level, then only 5 out of 100 samples would theoretically not have the population mean in there, right? 95 out of 100 would. So you have a very good level of confidence there. But we do always want to remember in stats that we're never proving something, right? We're just getting the best information we can based on the data we